Have you ever wondered what the universe sounds like? For all of human history, our relationship with the cosmos has been almost entirely visual. From the earliest stargazers looking up at the night sky, charting the movements of planets and the phases of the moon, to the magnificent, vibrant images beamed back by the Hubble and James Webb Space Telescopes. We have understood the universe by looking at the light it emits. We have mapped out sprawling galaxies containing billions of stars. We have watched radiant stellar nurseries where new suns are born from clouds of dust and gas, and we have peered to the very edge of the observable universe. We have achieved all of this by capturing different wavelengths of the electromagnetic spectrum. We see the universe in visible light, but we also see it in radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. But light, for all its revelatory power, has fundamental limitations. There are objects in the universe that emit no light whatsoever. They are cloaked in absolute darkness. The most famous and mysterious of these dark entities are black holes. A black hole is a region of space where matter has been packed so densely, and gravity is so overwhelmingly strong that nothing can move fast enough to escape its pull. Not even light itself, the fastest thing in the universe, can break free. Because they trap light, they are completely invisible to our traditional telescopes. You could point the most powerful optical telescope ever built directly at a black hole, and you would see absolutely nothing but the black void of space. If two of these invisible behemoths were to orbit each other, spiral inward, and violently collide, an event of unimaginable scale and power, our telescopes would be completely blind to it. Yet, we know that these colossal collisions happen frequently across the cosmos, and remarkably, we have finally found a way to witness them, not by seeing them, but by listening to them. We have built giant, incredibly sensitive ears on the surface of the Earth, allowing us to hear the faint echoes of the most violent events in the cosmos. But how do you hear something in the vacuum of space where sound cannot travel? And how on earth do you listen to a black hole? The answer lies in understanding the very fabric of reality itself. To truly grasp how we can hear the universe, we have to travel back in time over a century to the year 1915 AD, when Albert Einstein introduced his general theory of relativity. Before Einstein, the prevailing understanding of gravity was largely dictated by the work of Isaac Newton in the late 1600s AD. Newton described gravity as an invisible, instantaneous force pulling massive objects towards one another across a static, empty space. Space was just the empty stage on which the events of the universe took place. Einstein completely revolutionized this idea. He proposed that we should not think of space and time as separate, empty voids, but rather as a single, flexible, dynamic, and interwoven fabric called spacetime. Imagine spacetime as a tightly stretched rubber sheet or a large trampoline. If you place a heavy object, like a dense bowling ball, in the center of the trampoline, it will stretch the fabric downwards, creating a deep curve or dip. Now, if you take a smaller object, like a glass marble, and roll it across the trampoline, it won't travel in a perfectly straight line. Its path will naturally curve around the dip made by the bowling ball. If you roll it at just the right speed and angle, the marble will orbit the bowling ball, traveling along the curved slope of the fabric. Einstein realized that this curving of spacetime is exactly what we experience as the phenomenon of gravity. The Earth orbits the Sun not because of an invisible magical tether pulling it inward, but because the Earth is freely following the natural curves and valleys in the fabric of spacetime created by the Sun's immense mass. Spacetime tells matter how to move, and matter tells spacetime how to curve. But Einstein's elegant theory predicted something even more profound and bizarre. If a massive object is sitting still or moving at a constant speed in a straight line, it creates a steady, unmoving dimple in spacetime. However, if a massive object accelerates, or if two massive objects violently interact with each other, they shouldn't just bend the fabric. They should actively churn it. This churning would create ripples that travel outward in all directions at the speed of light. These ripples are called gravitational waves. Think of throwing a heavy stone into a perfectly calm pond. The sudden impact disrupts the water, sending concentric circular waves traveling outward across the surface until they eventually hit the shore. Gravitational waves are very similar in concept, but instead of rippling through a medium like water or air, they are literally rippling through the very geometry of space and time itself. As a gravitational wave passes through a region of space, it physically stretches and squeezes everything in its path. Space itself is distorted. If a powerful gravitational wave were to pass through your body right now, you would briefly become taller and thinner as space stretches vertically and squeezes horizontally. And then, a fraction of a second later, you would become shorter and wider as the wave oscillates. You wouldn't feel it because your bones, your cells, and the very atoms making up your body would be stretching and squeezing along with the space they occupy. In 1916 AD, just a year after publishing his general theory of relativity, Einstein mathematically proved that these waves must exist based on his equations. However, he also calculated their expected strength, and the results were discouraging. Gravity is an incredibly weak force compared to the other fundamental forces of nature, like electromagnetism or the strong nuclear force. Because the fabric of spacetime is incredibly stiff and resistant to being deformed, it takes a truly astronomical amount of energy to create even a tiny, barely perceptible ripple. Einstein concluded that by the time any gravitational waves from distant cosmic events traveled across the vastness of the universe and reached Earth, they would be so infinitesimally small that they would be absolutely impossible to measure with any conceivable technology. The stretching and squeezing would be on a microscopic scale much, much smaller than a single atom. For decades, the global scientific community largely agreed with him. Gravitational waves were viewed as a fascinating mathematical curiosity, a neat theoretical feature of relativity, but something we would never, ever be able to physically detect or observe. It takes something truly cataclysmic, an event of incomprehensible violence, to create gravitational waves that are even remotely detectable by the time they cross millions or billions of light-years of space to reach us. You need the most massive objects in the universe moving at the highest possible speeds. This brings us directly back to the enigmatic black holes. Imagine two stellar mass black holes, each dozens of times more massive than our own Sun, but compressed into spheres only a few dozen miles across. They are locked together in a deadly binary orbit, bound by their mutual gravitational attraction. For millions of years, they slowly spiral closer and closer to one another. As the distance between them shrinks, their orbital speed increases dramatically. In the final, chaotic fractions of a second before they finally collide, they are whipping around each other at a significant fraction of the speed of light. This frantic, incredibly violent dance violently churns up the local fabric of spacetime, radiating colossal amounts of kinetic energy outward in the form of gravitational waves. Finally, the two black holes merge into a single, even larger black hole. In that final, explosive moment of collision, the power released in the form of gravitational waves is absolutely staggering. For a brief instant, the energy output of that single invisible collision is greater than the combined light emitted by every single star in every single star in every single galaxy. In the entire observable universe, it is an event of unmatched fury. But again, despite all this energy, no light is produced. Telescopes see nothing. Only a silent, invisible tsunami of distorted space-time expanding outwards in all directions into the cold, dark cosmos. By the time these ripples from a distant black hole collision traverse the immense void of intergalactic space and finally wash over our tiny planet Earth, they have lost much of their intensity. They are spread incredibly thin. The change in distance they cause here is mind-bogglingly small. To detect them, we need to measure a change in length that is roughly 1/10,000th the width of a single proton. The proton is the positively charged particle at the center of an atom, already impossibly small. To put this required precision into perspective, imagine trying to measure the distance from Earth to the nearest star system, Proxima Centauri, which is about 4 light-years away, or roughly 24 trillion miles. You would need to measure that unimaginably vast distance with an accuracy equal to the width of a single human hair. It sounds like an impossible task. How could human engineers and physicists possibly build a ruler that precise? How do you measure a change in distance smaller than the fundamental building blocks of matter? The answer is a marvel of modern engineering called the Laser Interferometer Gravitational Wave Observatory, or LIGO. The fundamental concept behind LIGO is at once brilliantly simple in its physical theory and terrifyingly complex in its real-world execution. An interferometer is a device that uses the interference properties of light, waves to make incredibly precise measurements of distance. Imagine an enormous ground-level facility shaped like an L. It features two perfectly straight, concrete-covered vacuum tubes called arms, extending outwards from a central corner station at exactly a 90-degree angle. Each arm is exactly 4 kilometers, or about 2.5 miles long. Inside the central corner station of this giant L, a highly stable, high-powered infrared laser beam is generated. This laser is fired at a precisely angled device called a beam splitter. The beam splitter is a specialized mirror designed to let exactly half the laser light pass straight through into one of the 4-kilometer arms, while reflecting the other half at a right angle into the second 4-kilometer arm. The two identical laser beams travel down the long vacuum tubes, hit highly polished, ultra-reflective test mass mirrors suspended at the far ends, and bounce all the way back to the central beam splitter. When the two beams recombine at the corner station, their optics are carefully aligned so that their light waves perfectly cancel each other out. Light travels in waves with peaks and troughs. If you line up the peak of one wave with the trough of another identical wave, they undergo destructive interference, completely neutralizing each other and resulting in complete darkness. A sensitive light detector sits directly where the beams recombine. Under normal, quiet circumstances, it registers absolutely nothing. The system is perfectly, delicately balanced in darkness. This precarious balance is where the magic of the gravitational wave detection comes into play. As a gravitational wave from a distant black hole collision washes over the Earth, it stretches space in one direction while simultaneously squeezing it in the perpendicular direction. If this wave passes through the LIGO facility, it will momentarily stretch the physical length of one of the 4-kilometer arms while simultaneously squeezing the other. Then, a fraction of a second later, as the wave oscillates, it will stretch the squeezed arm and squeeze the previously stretched arm. Because space itself is dynamically changing size, the actual physical distance the laser light has to travel in each arm changes. One beam suddenly has a slightly further distance to travel, while the other beam has slightly less distance to cover. Because the travel distances are no longer perfectly identical, the two returning laser beams are knocked out of phase. They no longer cancel each other out perfectly when they A tiny, fleeting flicker of light escapes the destructive interference and hits the detector. By precisely measuring the intensity and timing of that incredibly faint flicker of light, scientists and supercomputers can determine exactly how much the arm stretched and squeezed, and from that data, deduce the exact shape, frequency, and amplitude of the passing gravitational wave. Building a machine sensitive enough to do this required pushing the absolute boundaries of human technology, materials, science, and quantum physics further than ever before. The physical challenges were immense. The mirrors used to reflect the lasers are massive cylinders of ultra-pure fused silica glass, weighing almost 90 pounds each. They are suspended by fine, delicate glass threads to isolate them from the constant, rumbling seismic vibrations of the Earth. The surface of these mirrors is so perfectly polished and uniform that they are among the smoothest objects ever created by humanity. If you were to scale one of these mirrors up to be the size of the entire Earth, the tallest mountain or bump on its surface would be only an inch high. Furthermore, the 4-kilometer tubes the lasers travel through are pumped completely free of air, creating one of the largest, purest, and most sustained vacuums on the planet. This is absolutely necessary to ensure the laser light is not scattered or distorted by randomly drifting air molecules. The engineers had to account for and filter out an endless stream of environmental noise. Microscopic, localized earthquakes, the rhythmic crashing of ocean waves hundreds of miles away on the coast, the rumble of heavy trucks driving on distant highways, the wind blowing against the buildings, and even the tiny, random quantum fluctuations of the laser light photons themselves pushing against the heavy mirrors. To make absolutely sure a detected signal is real and not just a localized disturbance, like a dropping tool or a minor tremor, there isn't just one LIGO detector. There are two nearly identical observatories in the United States. One is located in the desert shrubland of Hanford, Washington, and the other is located over 1,000 miles away in the pine forests of Livingston, Louisiana. A true gravitational wave passing through the Earth at the speed of light will hit one detector and then, roughly 7 to 10 milliseconds later, hit the other. If both detectors independently record the exact same microscopic stretching and squeezing pattern at the correct time interval, scientists can confidently conclude they have captured a genuine cosmic event and not just local noise. Now, how does all of this incredibly complex laser physics relate to sound? How do we take this data and literally hear it? The answer lies in the frequencies of the waves. The gravitational waves that LIGO is specifically designed and tuned to detect happen to oscillate at frequencies that fall squarely within the range of human hearing, roughly between 20 and 2000 Hz. When the laser detector measures the alternating stretching and squeezing of the arms over time, it produces a specific wave pattern. If you take that wave pattern, the changing amplitude and frequency over a period of time, simply run it through a speaker or a pair of headphones, instead of plotting it visually on a graph, you produce a sound. You are literally taking the vibration of the fabric of spacetime itself and translating it directly into the vibration of air molecules that your biological ears can process and hear. When two black holes are in the early stages of spiraling toward each other, they are moving relatively slowly and are still quite far apart. In this phase, they produce low-frequency, long-wavelength gravitational waves. If we played this early data through a speaker, it would sound like a very low, deep, almost imperceptible rumble. As the black holes get closer and closer, their mutual gravitational pull accelerates them. They spin around each other faster and faster. Consequently, the gravitational waves they churn out increase in both frequency and amplitude. The rumble becomes a higher pitch and gets progressively louder. In the final catastrophic fraction of a second, as they reach their maximum possible speed and violently smash together, the frequency of the waves spikes dramatically before abruptly stopping entirely as the newly formed single black hole settles down into a quiet, perfect sphere. When you translate this very specific, rapid frequency spike into audio, it produces a very distinct, characteristic, and now famous sound. It starts as a low tone and rapidly sweeps up in pitch before abruptly cutting off. Scientists call this distinct audio signature a chirp. It sounds remarkably similar to a bird chirping in a quiet forest, or a single drop of water falling into a puddle. This tiny, seemingly innocuous chirp is the direct auditory translation of two of the most destructive, massive, and mysterious objects in the universe merging into one. It is the final violent death cry of two black holes broadcast across the universe. On September 14, 2015 AD, after literally decades of meticulous planning, designing, building, testing, and refining the incredibly sensitive instruments, the upgraded advanced LIGO detectors were turned on for a new official observation run. Almost immediately, before they had even fully calibrated the system, the detectors in both Washington and Louisiana simultaneously picked up a clear, undeniable signal. It was a perfect, unambiguous chirp in the data. The observed waveform exactly matched the theoretical predictions made by massive supercomputers simulating black hole collisions based on Einstein's equations. By carefully analyzing the precise shape, length, and pitch of the wave, scientists could determine the exact nature of the cataclysmic event. They discovered that approximately 1.3 billion years ago, a time long before multicellular life had even evolved on Earth, two massive black holes had found each other. One was roughly 29 times the mass of our Sun, and the other was 36 times the mass of our Sun. In the final, blindingly fast moments of their merger, they combined to form a new black hole 62 times the mass of the Sun. You might notice the math doesn't quite add up. The missing three solar masses were instantly converted purely into gravitational wave energy. In a fraction of a second, those violent ripples traveled outward through the cosmos for 1.3 billion years, passing right through galaxies, stars, and nebulas, completely undisturbed, before finally washing over the Earth on a quiet September morning, changing the length of LIGO's concrete arms by a fraction of a proton, and creating a tiny historic chirp in the data streams. This detection was instantly recognized as one of the greatest scientific achievements in human history. It finally, definitively proved a 100-ril prediction made by Einstein in 1916 AD, but far more importantly, it fundamentally and permanently changed how humanity interacts with the universe. Before 2015 AD, humanity was effectively deaf to the cosmos. We could only look at the stars in silent awe. Now, we have ears. The era of gravitational wave astronomy has officially begun. We are no longer limited to studying only the objects that happen to emit electromagnetic radiation. We can now actively probe the dark, invisible side of the universe. Since that first historic chirp in 2015 AD, LIGO and its growing network of sister observatories, like Virgo in Italy and Kagra in Japan, have detected dozens of other black hole collisions. We are rapidly beginning to map out a massive, hidden population of black holes that we never could have found with traditional telescopes. We are learning how black holes form, how they interact, and how often they collide in the vast depths of space. But the excitement doesn't stop with black holes. In 2017 AD, the global network of detectors picked up a very different kind of signal. It was a much longer, higher-pitched chirp, lasting over 100 seconds instead of a fraction of a second. This indicated a collision between two objects that were much less massive than black holes, but still incredibly dense. These were neutron stars, the collapsed ultra-dense cores of dead giant stars. When these two neutron stars collided, they not only produced a massive storm of gravitational waves, but they also violently erupted in a blinding explosion of light and radioactive matter. Because they emitted light as well as gravity, telescopes all over the world, on the ground and in space, were able to quickly point to the exact location of the collision and watch the glowing aftermath unfold in different wavelengths of light. This single, incredible event birthed a brand new, revolutionary field called multi-messenger astronomy. For the very first time in human history, we could both hear the initial collision through the medium of gravitational waves and then see the fiery aftermath through the medium of light. It's exactly like watching a distant thunderstorm. You first see the flash of lightning, and then you hear the delayed boom of thunder. Combining those two distinct senses gives you a vastly more complete and detailed picture of the event than either sense could provide on its own. By studying the light from that neutron star collision, scientists were able to definitively confirm a long-held theory: that these extreme cosmic crashes are the literal cosmic forges where the heaviest elements in the universe, like gold, platinum, and uranium, are created. The gold in a wedding ring, or the platinum in a catalytic converter, was literally forged in the violent, explosive collision of two dead stars billions of years ago. And we know this for a fact because we can now listen to the ripples in spacetime. As our detectors on Earth become even more technologically advanced and sensitive, and as we look toward launching enormous gravitational wave detectors into space, like the European Space Agency's upcoming LISA mission, we will be able to listen further out into the universe and deeper into the ancient past. We might soon hear the continuous low-frequency hum of millions of distant white dwarf stars orbiting each other in our own galaxy. We might detect the explosive, violent death throes of massive giant stars deep within their cores as they collapse into black holes, before the light of the supernova even reaches the surface. We may even one day be able to detect the faint primordial background noise of gravitational waves left over from the Big Bang itself, the literal echoing sound of the universe's explosive creation. For countless centuries, our understanding of the cosmos has been strictly confined by what our eyes and our optical instruments could see. We have been watching a silent movie of the universe. Now a grand, chaotic, and beautiful new symphony has opened up to us. The universe is speaking. The very fabric of reality is vibrating with the stories of unseen cataclysms, invisible monsters, and ancient explosions. And for the very first time since the dawn of humanity, we are finally listening to the music of the cosmos.